Esteemed listeners, today we will present algorithm efficiency analysis and the fundamental aspects of algorithm efficiency analysis. The portion that I am going to discuss in this tutorial is very crucial for the further understanding of this subject titled Design and Analysis of Algorithms. Okay, any algorithm written by an algorithmist should be subjected to efficiency analysis. By efficiency we mean the algorithm analysis. As a matter of fact, analysis, the word analysis would mean separation of an intellectual or substantial whole into its constituent parts for individual study. That means when we do analysis of anything, any entity or any process and algorithms over here, we are going to come out with some inferences or some other thing. Okay, some other thing. Okay, so therefore algorithm efficiency would only mean examining the efficiency of the algorithm with respect to two resources. One, the space efficiency, the other, the time efficiency. Okay, by space efficiency we mean, analysis of space efficiency we mean how much extra space an algorithm consumes when compared with some other algorithm. It's of course these are all relative terms. Okay, when compared with some other algorithm, how much extra space this algorithm consumes. So also the same definition, in the same token, time efficiency would mean what is the extra time consumed by the algorithm when compared to other algorithm. Okay. Anyway, space efficiency and time efficiency are to be determined for a given algorithm. These two determinations comes from the fact that we have been given, let us say, umpteen number of algorithms which are boasting of solving a same problem. So in such cases, selection of the best algorithm remains an open question. Therefore, in that particular case, we need to apply efficiency analysis, and efficiency analysis is done in two ways. As far as two aspects, two resources. I should say two resources. One is space efficiency, other one is time efficiency. One is space and other one is time. Of course, nowadays, a decade ago, or 2 decades ago, I still remember for having analyzed algorithms for space efficiency. But with the advent of computer space, computer memory space, okay, computer technologies, of course, space is available at a much cheaper rate. Therefore, there is no need to analyze any algorithm for space efficiency for this simple reason. Okay, space is available in abundance for relatively cheaper rate. But however, the time, okay, the processor time specifically told, the processor time is available at premium even till today. Therefore, time efficiency is a must. Okay, analyzing for time efficiency not only determines how much extra space the algorithm consumes, a faster running algorithm will also an indicator of the intellectual power of an algorithmist. It's an indicator of intellectual power of an algorithm, power of a algorithmist, intellectual power. It speaks of intellectual power because algorithm is a notion. Okay, algorithms are developed in a mental framework. Long ago, say around 2 decades back, both were available at a very high premium, and nowadays it's only time that we should worry about. Okay, and why we should worry about time efficiency? Okay, this is the memory hierarchy in a typical computer. Here are the registers which will be able to execute arithmetic expressions, conditions, and arithmetic operations. Okay, logical operations, and everything will be done over here at a very faster rate. And then comes cache memory. In cache memory, the processes which are yet to go for the register will be queued up, or the processes, the outcomes of a process uh, which are yet to go to main memory will be queued up over here. Therefore, it stands as a via media between main memory and register memory. And it is very important to realize that a register can never converse directly with the main memory, and there is no direct interprocessor communication between register memory and main memory. And cache can only talk to main memory, and it can draw instructions and data from the main memory, and it can port it to register memory. And register memory is quite a small place, and the cells of and the smallest units of register memory will never come with address locations. Therefore, I think you should recall that whenever we declare the variables under register category, we will never read them with ampersand. Okay, because they do not, there is no concept of providing address locations for the variables which are in the register. So a program developer will always declare register variables to be register variables only for those variables which will be repeatedly executed in a loop. So much so that we can increase the speed of a loop, execution of the loop. And even if you declare too many variables under register category, it won't take it. It is just like that. Okay, and main memory can talk to auxiliary memory. Auxiliary memory will have a very huge space in. So if you come in this direction, there is an increase in the space and decrease in the cost. If you go in the upward direction, there is an increase in the speed and also increase in the cost. Okay, cost per bit increase, and here goes volume increase. Okay, therefore this is at a premium. Register memory is at a premium, and you should develop a computer algorithm for solving a problem in such a way that it will remain in registers for a considerably small amount of time when compared to any other algorithm. Then only we can boast of having designed an algorithm which would take a lesser amount of time when compared to other algorithms. Okay? Therefore, this is the reason why still design and analysis of algorithms is a core subject in most of the Indian universities and elsewhere also, because it will give some kind of an ability for an algorithmist to design or to solve a problem in a more intelligent fashion, so that it would consume lesser amount of time when it is when it is translated as a high level language translated program. Okay, the time, speed and cost are still at premium. Therefore, every algorithm deserves an analysis with respect to time efficiency. Right. The time efficiency analysis can be done adopting any two strategies. There are two techniques available in order to analyze the efficiency of an algorithm. Number one, posteriori analysis or posterior analysis. Number two, priori analysis or a priori analysis. Okay, as far as posterior analysis, postmortem, posthumous. The award was given posthumously after something, after the happening of the something. Okay, what something happens over here? You have already written the algorithm. Okay, you convert the algorithm into a program, execute the program, and literally measure the time taken by the program. This can be done. There are functions available in any high-level language, so much so that you will be able to measure how much time it has taken to execute a process, to execute a procedure, to execute a program, therefore to execute an algorithm. Okay, therefore you can directly measure. But there are lot of questions that are to be posed. Okay, a algorithm which is verbose, a program which is verbose, okay, and you have a system which is a sophisticated system, let us say, the architecture is excellent, state-of-the-art architecture, it would run within no time. Okay, therefore, a program, whether it gets executed fastly or slowly, depends upon the architecture of the machine, number one. Number two, if you choose some of the languages for running your program, it will let us say interpreter based languages, they will run slowly. But if you consider C, C++ and Fortran, they will make the program to run faster. That is the virtue of the language itself. Therefore, if an algorithmist has written a program which is intelligent enough to be able to run within a short duration of time, but having translated this particular algorithm into in a language like Java or like any other language, interpreter based language, it will run slowly. So in this case we are underestimating the intellectual nature or intelligence that is poured into this particular algorithm. On the other hand, it will be other way around. Okay, a small program, short program can take much of time if it is made to run in a age-old computer, let us say, of a lower architecture. So therefore, posterior analysis uh, leads to some of the factors that are to be considered. Extraneous factors are to be considered, and we will never measure the problem solving, the intelligent problem solving that has happened in the particular algorithm. Okay, essentially we will never measure the time efficiency. We will measure the efficiency of a language maybe, or efficiency of a system, efficiency of an architecture of the system. Therefore, we are not answering to this particular question. We are not doing whatever that we wanted to. Therefore, this is ruled out. Posterior analysis is ruled out. It is always a priori analysis or priori analysis that will be done on an algorithm. Write the algorithm. Steps goes like this. Write the algorithm. Make a theoretical analysis. Okay. Determine the time complexity as an indirect measure of time consumption. Use this information to select the best algorithm from among the host of algorithms. After all, we do efficiency analysis only to select best of the algorithms among algorithms which have been written in order to solve the same problem. Because we have understood in the first tutorial itself, there can be many algorithms to solve the same problem. But when it comes to the selection, we need to analyze every algorithm, any algorithm and every algorithm for its time efficiency. Okay, so now it is fixed that we will be doing priori analysis. Okay, so priori analysis of non-recursive algorithms. Okay, I repeat once again, a priori analysis or priori analysis of non-recursive algorithms has to be done in a framework. Okay, it is universally defined. This framework is universally defined, and every non-recursive algorithm should be analyzed under this framework. Okay, there is a different strategy, different methodology as far as recursive algorithms are concerned. We will go to that. We will come to that point. Okay, in a short duration of time, of course. Okay, and this frame of analyzing the algorithm comes with two steps. One, measuring the input size. Two, units for measuring the running time. Okay, measure the input size as the first step and find the unit for measuring the running time. Then it is done. Okay, measuring the input size. How do you measure the input size? We never bring a tape that is being used by a tailor to measure the input size. It is not expressed in meters, not expressed in centimeters or millimeters either. Okay, it depends on the input of the problem. The input size depends upon the problem exactly. Okay, if it is a polynomial, for example, if you are solving a polynomial of a certain degree, okay, the input is of degree n, let us say, the input is n plus 1. For example, the degree of the polynomial here is 5, therefore we need to input a, b, c, d, e and f, constant term. Okay, these are all 5 values and this is the last value, this constant value. Therefore, it needs 5 plus 1 inputs. Okay, that is the input size. If it is a matrix related problem, like graphs, like trees, okay, like some, okay, like assignment problem, there are many problems in operation research, okay, which are based on matrix manipulation. So if the problem is related to, or if the problem uses a matrix, then size of the matrix or order of the matrix is the input. If it is an array related problem, if array is the input, then size of the array is the input. And if it is a graph related problem, we need to make use of two inputs. Okay, we need to define two input size. One is what is the size of vertex set and what is the size of edge set, because graph is an amalgamation of a binary relationship between vertices and edges. Okay, therefore vertex, the cardinality of vertex set, the cardinality of edge set remains to be two inputs as far as a graph related problem is concerned. If it is a tree related problem, it is definitely number of nodes in the tree, number of nodes in the tree, because various functions of a tree, okay, various operations of the tree can definitely be expressed as a function of node, function of number of nodes. And if it is a problem related to numbers, like finding GCD, finding LCM, finding factorial of a number, or finding a prime number, checking a prime number, these kind of problems, we need to consider the input as how many bits it is required to represent this particular number in bits. Okay, and for that there is a formula. Okay, number of bits required to represent a decimal number is given by, I think something is missing over here. Okay, that is nothing but the floor. Okay, the floor of, okay, log 2n plus 1. Okay, let us say if 15 is the number, okay, log 15 to base 2 is 3 point something. Okay, let us say 3 point something, and here is the floor. Okay, floor, I have explained this floor in my previous tutorial. It is the greatest integer which is less than this. Okay, it is 3.5 something, therefore the greatest integer is 3, therefore 3 plus 1. Okay, the number of bits required to represent 15 is 4. Like this, for any number you can calculate number of bits, and that forms the input size for a problem which deals with numbers, number theoretic algorithms. And why do we measure the input size? This is the basic question that we have to pose, that we have to put forth. Because we normally understand, it is natural to understand that more is the input size, slower will be the algorithm. Less is the input size, faster will be the algorithm. As the input size increases, the algorithm tends to become slow. Okay, as the input size decreases, the algorithm tends to become fast. Okay, therefore the time efficiency, the formalism that you want to bring for time efficiency is definitely a function of input size. Okay, definitely a function of input size. Therefore we need to bother about this. Right. Next step is measuring the running time, units for measuring running time. We need to find out units for measuring running time. Naturally, it will not be in seconds. It will not be in milliseconds either. Okay. Then how do you measure? We have written over here units of measuring running time, being the second step of algorithm time efficiency. Okay, a priori algorithm efficiency. Okay, not in seconds, not in milliseconds. Okay, one way is to count all the steps. Associate each step with a unit time. Let us say there are 100 steps, 100 lines in the program. So 100 into some units. Let us say some unit, maybe in the form of a formula. Let us see what. Okay, a unit of time, maybe 1 second, 1 millisecond, whatever. You multiply that by so many numbers, then you express. This is one of the ideas. But it will become drudgery. You have to count manually number of lines, and you have to put it. And it may so happen that in the places of inputs, okay, if the corresponding line, and if the coding line is input, it all depends upon the user. It all depends upon the algorithmist himself. Because if he takes time to input, it cannot be considered as a time. It cannot be considered as a running time of the algorithm. Okay, and there may be delays possible. Okay, therefore this step will become excessively difficult. It includes some primitive steps too. Therefore, it is essential it is essential that we should consider a basic operation. We should consider the basic operation. We have to identify the basic operation, and then we have to measure how many times a basic operation is getting executed. So, uh, by basic operation we mean it is the operation which consumes most of the algorithm time. I repeat, basic operation is that operation which will consume most of the operating time, most of the algorithm time, most of the algorithm. Usually basic operations will find maybe in a nested loop, maybe in a loop, okay, maybe in a loop. They will never appear in running statements or running steps. They will appear, usually they will appear in a loop, particularly in a nested loop. Okay, they will be lurking in some corner of a loop. What is this basic operation? Basic operation may be comparison, basic operation may be arithmetic operation, basic operation may be some relational expression, whatever. Okay, and we need to identify. It is in the hands of the algorithmist to decide as to what is the basic operation. And without this basic operation, that algorithm doesn't hold water. Okay, it is this basic operation where entire logic of this problem solving lies. Therefore, it is very important. Usually, basic operations gets repeated iteratively. Okay, we define the basic operation as the operation which would consume most of the algorithm time. Okay, most of the algorithm time. Right, and we will come to a formalism. We will try to develop some kind of a metric for measuring the running time. That's how we started. Okay, therefore it can be further taken like this. Therefore, and you will be considering only basic steps in an algorithm. Then we will put forth a formula, something like this. Okay, times consumed by an algorithm as a function of input size. Time consumed by the algorithm as a function of input size is approximately equal to okay, the unit of time that is consumed in order to run basic operation one time. Okay, I repeat, COP is the unit of time taken to run a basic operation only one time. But in an algorithm, you will find basic operations getting executed many times. Therefore, we need to count how many times basic operation is getting executed as a function of input size. See, input size surfaces over here in the very second step itself. It repeats here, it comes over here. Here we will have used this input size to express total time consumed by the algorithm as a function of input size, and here count of number of times basic operation is getting executed as a function of input size. Okay, and this comes like a formula. Anyway, this comes like a formula. Let us say in your algorithm there is a nested loop of degree 2, and in this nested inner for loop there is a basic operation. Then C of n will become n square. And in some other algorithm, the basic operation is available in the innermost loop, innermost repetitive structure, okay, which is third degree, okay, nested loop. Okay, therefore this will become n cube. And there is only one for loop. There is a basic step. Therefore, since the basic step decides or consumes most of the algorithm time, and this is important. Therefore, C of n is also a function. This formula is approximate because it should be used very cautiously. Of course, it can be used because we will analyze all the algorithms that has come to our table to find out the best possible algorithm, and we will exercise the same thing. Therefore, we are not committing any mistake. But anyway, this formula is approximate because we have not considered those steps which are not basic. Okay. Therefore, this formula is to be used with caution. Okay. it is used only to measure the running time of an algorithm, very approximately, in order to compare several algorithms. Okay, right. So we may seek to answer a very important question. Of course, two questions, out of which one is very primitive. The very primitive question is, we may ask, if at all an algorithmist is given a computer which is 10 times faster than what he has. I repeat, if at all an algorithmist is given a computer which runs 10 times faster than what he has, then what is the speed? What is the speed of the algorithm? It will be 10 times faster, that's all. But we need not have to qualify a computer here. We have to qualify an algorithm to be time efficient, as an efficient algorithm. Therefore, we never seek to answer such kind of questions. We seek to answer better we seek to answer a kind of a question something like this. Okay, how much slower the algorithm will become if the input size is doubled? How much slower your algorithm will become if the input is made 3 times? Okay, so we will investigate this and we will see how exactly we will boil down to some kind of a metric which can be taken indirectly as running time of an algorithm, a measure of running time of an algorithm. Rather, let us say CFN in one algorithm has evaluated to be 2n square. There are two for loops of degree 2, and in both the for loops there is a basic step. Which will be consuming most of the algorithm time. Now I will express. Okay, the total time consumed by the algorithm as a function of input size is equal to unit of time consumed to run basic operation one time. Therefore, it becomes CO into 2n square. Now, I will double the input size. Okay, n is no longer n will become 2n. Then I will substitute over here t of 2n, time taken by the algorithm upon making the input size doubled. Is CO, 2 remains over here. In place of n, I will submit 2n, it becomes 4n square. Then I will take a ratio. Okay, total time consumed by the algorithm upon doubling the input size, and this was the de facto, that is the customary algorithm, the original algorithm, okay, for the natural input size. So this will be CO 8n square and this is 2n square. Okay, I will literally do this because there is some kind of an intricacy over here. There is some kind of an intricacy over here. This and this will get cancelled. Okay, n square will get cancelled, and 2 will give us 4. Only it emerges to be a number. This number is very crucial. This number is very important, and this number speaks volumes about your algorithm speed. Okay, this is a number. Okay, this number is called as order of growth. Okay, order of growth is an indirect metric of running time of an algorithm. It only tells by how many times order of growth will imply by how many times the algorithm will become slower on a double fold increase in the input size, or by a certain folds of increase of input size. As far as this example is concerned, the algorithm with a complexity 2n square will become 4 times slower upon increasing the input 2 folds. Okay, therefore order of growth is a metric. Okay, and we can generalize order of growth something like this: as the order of growth increases, the algorithms tends to become slower. As the order of growth decreases, the algorithm tends to become faster. Therefore, we are expressing some time units in an indirect way. Of course, in some unwritten terms. We may not be using seconds or minutes, but anyway, we are conveying the fact. And if there are two algorithms with different complexities, and if one algorithm says the order of growth of my algorithm is 4, and the order of growth of some other algorithm is 2, eventually the order of growth, the algorithm with order of growth equal to 2 will be selected, because it runs faster when compared to the other algorithm, even if the input size is double. Okay, to get a feeling for this, order of growth and how exactly the algorithms would blow up. Okay, here is a table. Okay, here is a table. We can present this table, right? And here there are various complexities written over here. This is linear. Okay, this is input size actually. Input size. This is input size in terms of numbers. In order to have some kind of a reinforced understanding, okay, we have given numerical example over here, and log to n. Okay, this is one of the complexities that we will come to know about this complexity. And at this point of time, at this juncture, you please be informed that it is possible to express the complexity of an algorithm by means of an algebraic equation, by means of a function, by means of a term, okay, by means of an expression, by means of a formulation. Anyway, log to n. Okay, this is the least possible complexity. Then linear complexity, n log n complexity, quadratic complexity, cubic complexity, exponential complexity, factorial complexity. I repeat, logarithmic complexity, linear complexity, n log n complexity, quadratic complexity, cubic complexity, exponential complexity, and factorial complexity. We will take input as 10. An algorithm with log complexity, a log n complexity, will take the basic operations getting executed only 3.3 times. But a linear complexity algorithm will run the basic operation will be running for 10 times. And if it is n log n complexity, it is 3.3 into 10 to the power of 1. If it is n square quadratic complexity, 10 square, that is 100 times your computer would have bothered. Okay, and it is n cube, 10 cube, 1000 times. 2 to the power of n, 10 to the power of 3, n factorial, 3.6 into 10 to the power of 6. It's a very huge number of steps. And 10 square, this will become 6.6. If the input size is 100, okay, it is 6.6, only 6.6 times. Okay, the basic operation gets executed. And this is 10 square, 100 times, 6.6 into 10 square, 10 to the power of 4, 10 to the power of 6. Okay, and here you look at this. Exponential complexity is huge, and factorial complexity is still huge. And the portion of this particular table is not at all filled, because of the obvious reasons. Okay, it will explode like this. Okay, it is huge complexity. Okay, if the input size goes on increasing, and we cannot have a feeling for this figure. Okay, how many times the basic operation gets executed. Okay, and we have understood during this tutorial as to what do we mean by efficiency analysis, why at all efficiency analysis is to be made, what are the three methods of analyzing efficiency. Time efficiency is important. We quoted space efficiency need not be taken that seriously. We quoted. And once again, time efficiency can be done in two ways. One is posterior and the other one is a priori. Posterior analysis is after writing the program, and it depends upon, rather than checking the intelligence and rather than checking the capability of problem solving, it is rather a check adopted to check the architecture of the system, and it depends on many extraneous factors that we need not have to consider. Therefore, it has been always time efficiency analysis. Okay, time efficiency analysis can be done under a framework, particularly for non-recursive algorithms. This framework will involve finding the input size or defining the input size and finding a unit for the running time. And the input size, it depends on the nature of the problem, while the running time comes out like a number, which is called as an order of growth. Okay, order of growth is an indirect metric of running time of an algorithm. Okay? And we also concluded by telling more the order of growth an algorithm suffers from, okay, slower it will be when compared to some other algorithm written to solve the same problem with a lower order of growth. So with this, friends, we will conclude. Okay, we will conclude. We will meet again for the next version of efficiency analysis. Until then,